There are two reasons why engineers and scientists may want to do things at smaller and smaller length scales. One of those reasons is that we can take advantage of phenomena at smaller length scales which we can at larger length scales. An example of that is something that's called the van der Waals force. As you can see, the van der Waals force is an attractive force between atoms or molecules, and it's certainly something that we notice in our everyday life. It's responsible for things like crystal structure, density, melting points, and boiling points. So the van der Waals force is a very, very important force at the nanometer scale. But if I think about forces at larger length scales, such as the meter scale that I'm more familiar with, the van der Waals force is much less important than forces like gravity, wind resistance, or friction that I'm used to encountering in my everyday life. So for a large number of years, the gecko baffled scientists because it had an ability to walk on vertical surfaces. You can see as early as 1901, scientists were trying to come up with different hypotheses about what gave the gecko this very unique capability. It wasn't until the invention of the scanning electron microscope that biologists were able to zoom in and look at very, very high magnification at the toes and feet of the gecko. On the next slide, we'll take a look at what they found. So what we're looking at here are higher and higher magnifications of the gecko's toe. At 30x, you may see something that looks similar to a human fingerprint. As we go to higher and higher magnifications, what we see here that each of the ridges of this fingerprint seem to be made up of tiny little hairs. At even higher magnifications, you'll see that each of those tiny little hairs seems to be made up of tiny little hairs. And if we go to the highest magnifications, at the tips of those very tiny little hairs seem to be tiny little hairs. If we continue to zoom into higher and higher magnifications, eventually we see that the smallest hairs of the gecko seem to be on the order of 100 to 200 nanometers in diameter. At this size scale, biologists hypothesized that maybe van der Waals forces or van der Waals interactions were what was responsible for the adhesive mechanism of the gecko. So based on this hypothesis that it was the van der Waals interaction that was giving the gecko this adhesive capability, scientists and engineers developed a very clever test to be able to see if their hypothesis was correct. Using MEMS technology, or microelectrical mechanical systems technology, they were able to create man-made or synthetic polymer hairs that were on the same size scale as the smallest hairs that they saw with the gecko. Okay, based on their theory that it was van der Waals interactions that were giving it this adhesive capability, they were able to predict the sort of adhesion that this sort of structure would be able to give based on a theory that it was van der Waals interactions. This suggests that scientists and engineers have developed a new adhesive mechanism that's bio-inspired and based on the mechanisms that geckos use. This mechanism is based on van der Waals interactions, and as you can see from the chart on the right, by tuning the pitch, the diameter, and the height of these individual fibers, they're able to very precisely tune the attraction between different surfaces.